Aloha class, this is Gigi. I am going over the length of curves. So suppose you have a function f of x, just like so, and we are looking at the length from A to B. Okay, so we're looking at the length from A to B of this curve here. And so just like how we were looking at the area, we're going to divide it up into sub-intervals. So then we're going to go and find, let's say, interval 1, length 2, length 3, and so on. And then we're going to add them up. So that's the general idea. Suppose we're looking at this particular length here. Let's call this L sub k, which is the kth piece in that length segment. And if we were to look at this here, we do have a right triangle, a tiny right triangle right there. So we'll blow that right triangle up and say the leg of the right triangle is delta x, and the other leg is delta y, right? Pythagoras will say that leg square plus the other leg square equals the hypotenuse square. So then the length L sub k that we are looking for is going to be square root of delta x squared plus delta y squared, which is what the Pythagorean theorem will give us. Okay, now I am going to do some fancy algebra here. And I'm going to go ahead and factor out the x squared. And as you can see, that delta x squared is on the denominator now because we factor out delta x squared. Okay. And then what we're going to do is we're going to go ahead, delta x squared, square root, square under square root. So delta x comes outside of the square root. And then so we will have that right there. And we are going to go ahead and sum them up from L1 to L sub n, right? There's nth little segments there. If we add them all up, that should give us a very good estimation. But what will give us a better approximation is if we had infinitely many subintervals. And when we do have what we see here, and we have seen this so many times already, limit as n goes to infinity of the sum from 1 to n of something, that is the definition of integral. So we would say the length, the actual length of the curve, that would be this length right here from A to B, is going to be defined as the integral from A to B of square root of 1 plus, and notice this right here is change in y over change in x, which is a slope. Slope of a function is a derivative, and a derivative square is what we have right there. Okay, so that is the equation on how to find the length of a curve. The integral from A to B of square root of 1 plus the derivative square dx. Now, let's go set up some integrals to find the length of these curves. For problem 1 through 3 in your guided notes, we are only asking you to set up the integral and not actually proceeding to evaluate. So when we look at this curve right here, sine of x from 0 to 2 pi, as you can see that there's symmetry. So if we just go from 0 to pi over 2, there is 1, 2, 3, 4 pieces that are the same. So we can say that the length is going to be 4 times the integral from 0 to pi over 2 of square root of 1 plus the derivative square dx. That's the equation on how to find the length, right? Now, we need to go ahead and say, hey, what is the derivative of sine of x? The derivative of sine of x is cosine of x. So the integral we are looking at is from 0 to 2 of square root of 1 plus cosine square dx. And we are going to multiply that by 4 because there are 4 symmetrical pieces here from 0 to pi over 2. And that is number 1. Now, the motivation here is to be able to find that integral. And that is in our next unit to learn how to evaluate integrals like this one. Okay, number 2. We are looking at the curve x e to the negative x, which would look like so. And we're looking at it from 0 to 1. Okay, so then we would say again, I would like to go ahead and review what just happened as far as how to find the length. We subdivided into different intervals, right? And then we look at one of them. Actually, all the little pieces, and they all have right triangles there. And within the right triangle, we would say, hey, let's just look at that particular piece right there. We have that triangle, and delta x, delta y would be the 2 legs, and the length that we're looking at right there is the hypotenuse. So Pythagoras would say leg square plus the other leg square equals to the hypotenuse square. So L sub k would be square root of delta x squared plus delta y squared. And we do some little fancy factoring out the square root delta x squared. And we will end up with this right here, right? And now we're going to sum them all up from 1 to n. And then we're going to take the limit as n go to infinity. So that really is how the integral of the length is born. The integral from 0 to 1 of square root of 1 plus the derivative square dx. Now, question is, what is the derivative of our function? X times e to the negative x. And when I said x times e to the negative x, we have to apply the product rule. And so the derivative would be e to the negative x minus x e to the negative x. And that right here is the thing that's going to go in there. So we will have the length of this curve from 0 to 1 is square root of 1 plus that derivative square dx. And again, our motivation here is how do we integrate? How do we integrate that derivative? And that is the lesson in the next unit. But for now, we can set up the integrals for the length of a curve. Number 3. Okay, if you take a look at this right here, it's half of a circle. So if we were to go from 0 to 1, that gives us this piece here, and the other piece would be the same length. So we can say there's 2 of those from 0 to 1. So then the length would be integral from 0 to 1 of square root of 1 plus the derivative square dx, and then multiply that by 2. Now we need to go and be able to find a derivative. The derivative of square root of x is 1 over 2 square root of x multiplied by the inside derivative. That's the chain rule, right? And we reduce that to be negative x over square root of 1 minus x squared. Now that is what's going to go inside right there. So we have the length is 2 multiplied by the integral from 0 to 1 of square root of 1 plus that derivative that we found, square dx. Right? Again, how do we integrate such thing? That is the motivation for the next unit. Next unit, we'll learn how to integrate these complicated integrals. Okay, number 4 is something we actually could write the integral and actually be able to evaluate. Okay, so again, let's take a look here. The length is integral from this case 0 to 1 of square root of 1 plus the derivative square dx. Now, what is the derivative of 1 of x to the 2/3 x to the negative 3 over 2? Well, if y is 2/3 x to the 3 over 2, then the derivative is, we would move this down, which 3 cancel with 3, 2 cancel with 2, we just have 1 x, and then 3 over 2 minus 1 is 1/2, which we say that is just square root of x. And that is the thing that goes inside there. So the length is, in this case, integral from 0 to 1, square root of 1 plus square root of x squared dx. Okay, that will just be the integral from 0 to 1 of square root of 1 plus x dx. Now, that integral is going to be 1 plus x to the, if we add, that's to the 1/2, 1/2 plus 1 is 3/2, and then we have to divide out the exponent, which is 2/3, and we are going to evaluate that from 0 to 1. So when we plug in 1, we will have 2/3 multiplied by 1 plus 1 is 2, square root of 2 to the 3rd power, that would be 2 square root of 2 minus 2/3 multiplied by 1 to the 3/2 would be 1/2. So that is going to give us, everything is over 3, that is 4 square root of 2 minus 2, and that is the length of that curve from here to here. So we just found this length right here to be 4 square root of 2 minus 2 over 3. That's pretty cool. We can find length of a curvy thing, not just straight things. Number 5. Okay, number 5 again. The length is integral from 0 to pi over 4, in this case, square root of 1 plus the derivative square dx. Okay, now we want to know what the derivative is. So y equals ln of secant of x. So then the derivative is, the derivative of ln of something is 1 over it being secant of x, multiplied by the inside derivative, which is the derivative of secant of x. And the derivative of secant is secant x tangent x. That's the inside derivative. This is going to cancel out. So this really is, the derivative is just tangent of x. So then the length, as we see here, is the integral from 0 to pi over 4, pi over 4, square root of 1 plus tangent of x squared dx. Now, if we remember the Pythagorean theorem, cosine square x plus sine square x equals 1. If we divide everything by cosine square x, we can see that 1 plus tangent square x is equal to secant square x. So this right here is just secant square of x. Now, square root will undo square, so then the length here is the integral from 0 to pi over 4 of secant of x dx. How do we integrate that? How do we integrate that? Okay, I'm going to go ahead and give you a sneak peek of what is ahead. There's a really good trick here to integrate secant of x. The integral from 0 to pi over 4, which is the length of secant of x, I am going to multiply by 1. And my 1 here is going to be secant of x plus tangent of x divided by secant of x plus tangent of x dx. Now, why did I do that? When I do this here, I will have the length equals integral from 0 to pi. On the denominator, I have secant of x plus tangent of x. On the numerator, I have secant square of x plus secant of x tangent of x. Do you see something yet? Why did I do that, and why is it helpful now? This right now is going to be a u substitution. Okay, so if we let u be secant of x plus tangent of x, the denominator, then du is secant square x plus secant x tangent x. That's the numerator, dx. So that right there basically is just the integral of 1 over u du, which is ln of u. That's a very nifty little trick, right? So this right here really is the length is equal to ln of secant x plus tangent x. And we are evaluating that from 0 to pi over 4. So when we plug in pi over 4, we will have ln of pi over 4. Secant of pi over 4 is 1 over cosine, and cosine would be square root of 2 plus tangent of pi over 4, which would be 1, minus ln of, plug in 0, you would have 1 plus tangent of 0. Tangent of 0. What's tangent of 0? Sine over cosine, that would be 0 over 1, which is 0. So ln of 1 is 0, so really we have the length is ln of square root of 2 plus 1. And that is our final answer for the length. So as you can see, the integral for finding the length of a curve can be very complicated. So that is being saved. Most of the application here is going to be saved for our next unit. So as your homework is going to be a little bit shorter, you're only going to be doing the ones that you could integrate, or we will only be asking you to set up and not solve. Okay, that is it.